Hmm. Um, I'll just go with three. All right. Okay, so question 3.1, we are asked to construct a tree. So yeah, and we are given forwards, bear, bell, Peter, and bite. Before we proceed any further, note that for every tree, it started out with a empty root node. All right, so yeah, we can just like put it down here first. There's an empty root node. Okay, and then for all the other four words, they all started with an alphabet B. So we know that directly beneath this empty root node, we would have a B node. And now, yeah, let's break down the words further by their suffix. So we can see that bar and bell, the common suffix is be, whereas for bitter and bite, the common suffix is like bit, just like beat. Okay, cool. Yeah, so this means that we can further break our tree into like these two main branch. Um, we have BE around here and then BI and T. Okay, once we have like fixed the suffix, yeah, let's break down the words even further. From the left subtree, we know that AR precedes LL, so we can just insert them. Whereas for the right subtree, we have bitter and bite. Like bite definitely precedes like TR. So we would start with bite first and then input the rest of bitter. Sorry, some typo. Yeah, so here's our tree. Okay, for question 3.2, we are given n words, each of length L on average. So what's the runtime of insertion? Speaking of insertion, we know that for any insertion operations, it involves two steps. First of all, it checks for existence, and second, it does the insert operations into the tree. Okay, for a given word, like the insertion operations also imply that there are two extreme cases. Like, for example, the first case would be that the word exists fully in our tree. On the other extreme end, it does not exist at all, like not even a single um, alphabet that's matched to what we have on the tree. So in case one, this implies that we have to traverse L nodes for each word, as we check through all the L nodes, just like alphabet by alphabet. For case two, since a word does not exist at all, this means that we have to add L alphabets or nodes into our tree, right? So as you can see in both cases, and when we have n words, like both cases will sum up to n times L, right? This means that our lower bound estimation equals to our upper bound estimation, and they are all n times L. So we can summarize the runtime as theta and L. Okay, for the last question 3.3, we are given a word with length L. And yeah, what's the runtime to check for the existence in our tree? So similarly, we can break this problem down into two extreme cases. The first one is that the word completely exists in our tree. On the other end, like on the extreme end, that is the word does not have a single matching alphabet at all. Okay, so let's go back to the first case. If the word completely exists in tree, this means that we must have visited L nodes in order to come to the conclusion that yes, the word completely exists in tree. On the other hand, like for example, if I have like given tree similar to the one in 3.1 and word is like alpha or anything that does not start with B, in that case, the maximum number of comparison is just one. So to summarize these both different cases, the upper bound approximation would be that, yeah, the word completely exists in our tree, so it would take runtime of L. On the other hand, the lower bound approximation would just be a constant time. So using our runtime notation, that is, an upper bound approximation can be summarized as big O, whereas a lower bound approximation can be represented as big omega. Yeah, so here's our answer. That is big omega 1 and big OL. Thank you.